Okay. Thank you.
Hello, Avril.
Yeah, hello.
Yeah, hi. Uh, do you have all the homeworks and all that with you in case they ask questions about that? I don't have that material here.
I have it open on the browser. Yeah.
Yeah. Okay, you can share it with me if they have any questions like that, right?
Yeah, yeah, yeah. Do the students join this meeting or are we just?
No, they are supposed to join this meeting. I made you a co-host, but this Zoom workplace, right? So they're supposed to join this.
Yeah, yeah, yeah. I've not fully checked all the week 10, which is the latest thing. Like,
Hmm.
I've checked everything else.
No, that's okay. That's okay. I don't know what they First of all, I don't know how many students will join. And second thing is, it might be in sort of general interaction. I don't know whether they'll ask specific questions.
Okay, yeah. Like, if there's any question that I think a lot of people can't do, then I put a solution on the chat group.
Okay.
Like, if I don't get a satisfactory answer from any of the people, I put it there myself.
You've been doing that. Huh? Yeah. Okay. Good.
Yeah.
How many are turning in their homeworks?
Up till week 9, it was a good number. It was like 14 people, I think. But last week, it's only been 11. And this week, it's been 10.
Okay. Well, yeah, that's fine.
It varies. Like, not all people submit all the homeworks.
And these are all registered students or not necessarily?
Actually, I haven't checked. Is there a way to check? I don't know.
Uh, how are they submitting homeworks directly to you or
No, no.
to the?
There's a portal where like you can just like there's a section after all the video lectures. There's a section for the assignment, and you can just upload your file there, and it
Oh, then
will
they
come to
have to
you.
be registered, right? For to upload homework?
No, sir. For exam registration, not mandatory, but they will register the course. So
No.
enrollment they will do,
Yes.
but exam registration, if they
Oh,
want to write the exam,
But homework is anybody can submit.
anybody can serve.
Okay, okay, okay. So yeah, okay.
But that will not count as a for certificate. So one who are writing the exam, they will submit the assignment.
Right, but homework is also given for marks.
Yes, yes, sir. For final score, they will
Yeah,
take
yeah.
assignments.
But to get a certificate, you have to write the final exam.
Both assignment and final exam.
Yeah. Yeah.
There's no people in the live stream also. Actually, I had a question.
Yeah.
So let me pull this up. Which assignment is this? So there was this like application of the regular value theorem. So we're given this function, this elliptic curve type thing. Yeah, this function f in two variables r2 to r, that was fxy equal to x cube minus 6xy plus y square. So, and we had to find all the values of C such that F inverse C was an embedded submanifold. So that's like the application of the regular value theorem. But the thing is that if you just apply the regular value theorem, you get a failure in two cases, but then it doesn't go the other way, right?
Yeah, it doesn't.
So there was two values, I think zero, F inverse zero and F inverse minus 108. And for both of them, we had to show that it wasn't a manifold and that wasn't like elementary and no one could do it. So was that the intended solution? Like, do you know the people who made the assignment?
Uh, I If it was zero, yeah. X squared plus y squared equal x squared plus y squared
It will
equal
be like if f inverse 0, it will be like an x intersection. So that's like that you have to show that there's just an x intersection, and then you can use path connectedness and whatever to show that this cannot be a one-dimensional manifold. And yeah, and for f
I
inverse
see.
minus 1, 0, you get an isolated point, and of course that
And
can't happen.
yeah, so that is yeah, 0. What is the other one? X squared minus 6xy plus what is the other singular value?
You mean the expression x cube minus 6xy plus y square, the singular values are 0 and minus 108.
Minus 1.
08.
Oh, minus 108.
Yeah, yeah, yeah.
That's a singular value.
Yeah.
Uh, Now, how do you get that number? See, the derivative gradient is just very simple, right?
Yeah.
Uh,
So the gradient is quadratic, right? There'll be two values.
so 2x minus 6y and 2y minus 6x. No, you'll get only one. You just set the gradient equal to 0.
Yeah, and that's all the regular values. Yeah.
Yeah, well, the gradient is 0 at at exactly 1 point, right?
No, no, it's a two. Like I can show you like using GeoGebra. Can you see this? Okay, maybe I should share my screen.
Yeah, share your screen.
Is this? Because like when I was taking this course, like from Professor Vamsi, I had the same question, and also like at that time I didn't.
No, for this quadratic polynomial that you mentioned, I don't think it's something more trivial that I think you just get only. Let me get it right. So is x squared minus 6xy plus y squared, is it?
No, x cube. Oh no, no, it's not x square. It's x cube.
Oh, okay.
Yeah. So that's the difference. Yeah, that's how you get to
X cubed minus, just
six
say
x
the word,
y.
yeah.
Yeah. Oh no, this is very like x square minus 6xy minus plus y square. In fact, I don't think will be a problem. Yeah. Yeah. Can you see my screen?
Uh, yeah, okay, fine. So, but
Yeah. So
okay,
this is
so
the equation here,
hmm,
and this is equal to c.
okay,
And if I put like c equal to 0, like
yeah,
this is the failure I'm getting. Yeah, this like self
yeah.
intersection.
Oh, nice. This is a very nice this thing. Okay.
And if I go to if I let this go to like, how do I do this?
Square minus 3
Uh,
square.
yes. If I let it go to 1 minus 108, then it's slightly more interesting. Uh, yeah. So this is what it looks like.
Well, it's looking like a smooth, I mean, smooth.
Yeah, so I initially thought, yeah, it's pretty smooth, that's good. But then when you do this, like when you go slightly close to, yeah, can you look at this? I mean, GeoGebra has some issue, but this thing, there's a loop here.
Hmm.
And when you go closer and closer to 108, you sort of lose the loop. It becomes a point, and that's the
But 1 second, so you can directly compute, right? X cubed minus 6y. The gradient is x cubed minus 6y. And oh, there's a y squared. Okay, so
yeah.
2
See
and then,
this thing when it goes to 10 minus 108, it shrinks to a point, and the points are not allowed.
oh, you get an isolated point, is it?
Yeah, it's an isolated point, so it can't be a embedded submanifold.
Can I, let me see. Oh, I should be able to open some. What app can I write on? Outlook?
I think there's a whiteboard option here.
Where?
Yeah, there should be an
Oh,
annotated.
whiteboard. Yeah.
Yeah,
Okay. New
yeah,
whiteboard.
yeah.
Oh, it says it will stop the screen share. Do you want to continue?
I mean,
Why should it
we have
stop?
seen this already, so I can stop it. Yeah.
Okay, let me just check. Why is nothing appearing here? Let me see.
Are you writing something?
Yeah, I'm writing something in this Wacom pen, but nothing is appearing here. I don't see Gurraja here. Okay, so I just
For some reason, it's not loading for me. Is that?
well, it says screen sharing share.
I think I stopped my screen share.
No, when I opened the whiteboard, it said it might automatically.
Yeah, I'm not screen sharing anymore. Yeah, but I can't see what you're writing.
Yeah, well, it's not writing, first of all. Do you see the whiteboard at all?
I'm like it's stuck halfway in the loading.
Okay. Sharing your screen will close the whiteboard for everyone. Do you want to continue? It's a very weird thing. Whiteboard should be also shared, right? Okay, now I closed it.
Yes. Oh, no, what's happening here?
Oh, there's a message. I would like to share this whiteboard from me. Maybe you would have to click that. Anyway, the whiteboard was not working. So just let me see. So it's a trivial thing anyway. So 6, what was it again? X cubed minus 6xy plus y squared, right?
Yeah, that was fxy.
So 3x squared minus 6y is the
Hmm.
first term in the gradient, and the other one is 2y minus 6x.
Yeah.
So second term is 0, means 2y equal to 6x, y equal to 3x. First term would 0 would mean that 3x squared equal to 6y. So x squared equal to 2y. Second one gave what? Y equal to 2x, right?
Yeah.
Y equal to, can you do this calculation?
Yeah, I'm doing it. So
Just
it's
calculate the gradient and set it equal to 0.
yeah.
Oh yeah, on my.
And this is minus. Yeah, so x square is 2y and y times 1 minus 6x is 0. Yeah. Yeah, so there's two equations. There's x square equal to 2y
Yes.
and there's y times 1 minus 6x is 0.
Y times y yeah, x squared equal to 2y.
Yeah, and y times 1 minus 6 is 0.
Y times 1 minus x.
Yeah.
No, the second term is 2y minus 6x equal
Oh, sorry. It is y minus
y
6x is
equal to
0.
3x.
Yeah.
So y equal to 3x, x squared equal to 2y.
Yeah. So there's one solution to this where
X
you will give
equal to
like
0 or x equal to 6.
yeah, it's
And
x square equal to 12x. That's the thing. So it has two
squared equal
solutions.
to 6x, not 12x.
X square is 2y and y is 6x.
No, y is not 6x. 2y equal to 6x. There's a y squared, right?
Oh, okay. I made another mistake. Yeah. So
So, uh,
x square is 6x. So x is 0
so
or x is 6.
the two critical points are x equal to 0 and y equal to 0.
Yeah.
and x equal to 6 and y equal to 18.
Yeah.
So x equal to 0, y equal to 0, that will give, that corresponds to the one, that singular set, yeah, corresponds to C equal to 0.
Yeah.
Oh, this is where you get that weird number, x equal to 6, y equal to 18.
Yeah. So
So
this is 6 cube minus
x cube minus 6y plus y square. 36 into 6 is 256, is it?
6 cube is 216.
Or 216.
Yeah, and this is 216 into 3.
This is, yeah,
And so that is like minus 216 into 2, which is 5 minus 532.
plus y squared is how much?
No, plus 432. Yeah, minus 432.
Oh, anyway, 6 can be taken common out of, actually 6 squared can be taken common out of the whole thing.
Yeah, so this is minus 432 plus 18 square, which is 324. Yeah, which is minus 108. So this evaluates to minus 108.
Oh, okay, fine. Yeah, fine. So this is, yeah, right. So this two singular values and the one with the singular value minus 108, you're saying it has an isolated point. How do you
Yeah.
see that directly from the equation? Well,
Yeah, I mean, it's just like the proving they're not manifolds is not very hard. You can just directly use the equations and it works out.
yeah, no, proving that it's not a manifold, it's easy once you figure out what the level set looks like. But
Yeah, so
how
I
do you,
couldn't do it if I didn't use GeoGebra. Like,
yeah,
I can,
exactly.
yeah,
That's what I'm trying to say. So how do you see directly that the second level set has an isolated point?
yeah. There was one assignment, this one AI generated one I sent you, which was using the Morse lemma. Yeah.
Oh man, those guys are going insane. Yeah. Let me just think. So how do you see it's an isolated point? Oh, right. Yeah. One way to see it's an isolated point is look at the Hessian at that point,
Mm-hmm.
right? So, I mean, that still won't tell you it's isolated, but
That is the Morse lemma, right? If you can characterize this using the behavior of the Hessian.
no, the Morse lemma applies if it is the Hessian is non-singular.
Yeah,
But
so,
so, for example, at that isolated point,
mm-hmm.
Hessian should also be Z. What will the Hessian look like? Yeah, what is the point? See, in the level set, uh, yeah, definitely Hessian will not. Yeah, no, it is possible. The Hessian,
Hessian
if the
looks
Hessian is
this,
non-singular,
right? 6x minus 6 minus 6, 2.
ah, Hessian is what is the matrix?
6x on the top left, minus 6 top right, minus 6 bottom left,
Uh,
2 bottom right.
2. Okay. So when x is 6, so this is 36 minus 6, 2, right?
Yeah,
Oh, this is non-singular.
yeah.
No,
But
then you should
the
not get
failure in
the.
this case is much better. Like in
No,
the
then
case
you
of,
should not get an. If Morse lemma applies, so this is,
yeah,
you should not get that isolated point because this has eigenvalues. So this is 72 plus 108. The determinant is 108. The trace is 38. So what are the eigenvalues? You should get real eigenvalues for this. Uh,
Are you getting real eigenvalues?
This is a symmetric matrix. You will always get real eigenvalues.
Oh, you're using x equal to 6.
Yeah, no, the Hessian is always a symmetric matrix.
Yeah, of course. But you're using x equal to 6.
Yeah, that is the one, right?
Yeah.
So what is that? If the derivative is zero at that point, then it's oh no. The Morse lemma just tells you what the function looks like near a singular near a singular point where the Hessian is non-singular. So the first derivative is zero.
Mm-hmm.
The Hessian is non-singular at this close to this. So that's the Morse lemma, right? It the first you have a function on a smooth manifold and look at a critical point of the function, and then yeah, in suitable coordinates, if you change coordinates, basically it tells you it looks like a quadratic. That's what the Morse lemma does.
Yeah, you
But
can. Like, there's some minus and plus signs there. I forgot the actual thing.
no, that's okay. But the point is, you cannot get an isolated point like that.
Because the failure
Isolated
in both
point.
cases is different. At x equal to 0, like you cannot like remove a point and make it embedded. But at x equal to minus 108, if you remove this thing, it is an embedded submanifold.
At x equal to 0, if you remove that,
If you
no, at
remove
x
the
equal to
point,
0, anyway, the level set itself is, I see. Oh, right. Yeah, the level set is not a singleton. Yeah, of course. Yeah, at x equal to 0, y equal to 0, it's just basically, some kind of, it's not an ellipse, but it's some kind of level set of a polynomial function which passes through 0, 0, right? You already said, yeah, it consists of that line.
yeah, it has
Yeah,
like
which
ellipse intersection.
basically
That's a
you
different
should be
failure.
able to factor this somehow, right? X cube
Yeah,
minus,
yeah, yeah.
how do you factor x cube? Well, no, forget that. Let's come back to the other one. At that 10 minus 108, the level set corresponding to this. Uh, yeah, it's kind of weird. How is that isolated point? I'm not sure that isolated point should come because yeah, think of it like this. Think of it like this. See, there is only one singular point here for that in that level set, minus 108 level set,
Yeah,
there should be only one singular point, x equal to 6, y equal to 18, right?
yeah.
Now, in that, according to the graphing app that you used, there are two components. One is a smooth curve. The other one is that isolated point.
Yeah.
Now, x equal to 6, y equal to 18, does it lie on that smooth curve or on supposed to be the isolated point?
Yeah, that's the isolated point.
Oh, that's the isolated point, is it?
Yeah.
But then,
And I can just show you the solution I wrote for the
yeah, according to the Morse lemma, then since the Hessian is, oh, you already, okay.
I gave the proof like because no one solved it. So like I just put it on the discussion channel.
Okay,
But I
let's see
didn't
what you
use
have
the
written.
Morse lemma. Like I just did it like by
The
hand.
gradient of f vanishes only at this thing, and removing this singular turns out to enough to make it into a smooth. See that there's a self f inverse 0. Yeah, f inverse 1 minus. This one is easier to show. Here the contradiction is that the point is isolated, also has a 1D. This violates the vector dimension. Okay, fine. Nobody seems to have turned, so I'm just discussing with my TA. Okay. So therefore, the discriminant, there's no y value. So keeping x constant, y equal to this. Y equal to this. At x equal to 6, y has only one solution, which is now. Oh, at x equal to 6, the thing under square root vanishes, is it?
Yeah.
Okay. So
the main thing is like because it's quadratic in y, I can just fix x and then I can solve explicitly for y. And in both the cases, I get different behavior. Like for the f inverse 0 case, I get like two curves, C1 and C2. And for the when minus 108 case, I get like just one single solution.
okay, this is a nice way of seeing it. Yeah. So you're saying that for non-zero x, the thing under square root is always negative, is it?
Yeah.
Uh,
I mean, near 6, near x
yeah,
equal to 6.
near x equal to 6. It's how does one see that?
I mean, for x equal to 6, it is
For x equal to 6, it's 0.
it's 0. And then you can take derivatives. I mean, this was one variable calculus, so I did not go into that.
So, oh, when derivative, so it's 18x minus 3x squared.
Yeah.
18x minus.
Which is which is x 3x and 6 minus x squared, which is negative.
3x into 6 minus x squared.
Yeah.
And if x is non-zero, if x is close to 6,
Yeah, then it is negative.
then, oh, because of this, no, well, if x is less than 6, it is positive.
No, it is 6 minus x squared, right? Not 6 minus x.
6 minus x squared, right? Yeah.
Yeah.
So if x is close to 6,
Yeah,
oh,
this is roughly 6 minus 36. Yeah.
I see. Yeah. Okay. It's not x. Yeah, it's x squared. Right. Right. Oh, yeah. If x is close to 6, there's always negative. Yeah. So
Yeah, the
this.
failure is like pretty bad. Yeah, it's not.
Oh, so it's always negative. So if x is close to 6,
Yeah. I
except
didn't give a rigorous proof, but yeah, I'm
if
just.
x equal to 6, it's 0. No, at x equal to 6 also, it doesn't look like it is. Oh, this is the derivative. Okay.
Yeah, this is the derivative. Yeah.
No, but at if everywhere it's negative and x equal to 6, it is 0, then
Yeah.
derivative should vanish at 0, at 6, right?
Because that will be a local maximum.
Yeah, but it doesn't look like that from this expression.
Okay, then that is true. Uh,
18x
Let's see.
minus 3x squared. So that is 3x into
Oh,
6,
it is that because the derivative is 18x minus 3x square.
right?
So yeah, so you can take 3x
Oh, it is
common.
3x. It is no,
Yeah,
it is the 6 minus x, not 6
yeah,
minus
yeah.
x
It's
squared.
3x times 6 minus x.
Yeah. So now if x is close to 6, if x is greater than 6, it is certainly negative.
Yeah,
But if x is less than 6, it's positive.
yeah.
So that doesn't quite. So your argument is not quite right because,
I mean, it has to be right because it cannot have any solutions near 6.
well, that's what you're trying to show.
Yeah, like if you assume the
If
thing.
you assume the graph is correct, but I'm a
Yeah.
bit skeptical of that, to be honest.
Oh,
Yeah,
okay.
yeah, that's why I'm doing all this.
Oh, okay, okay, yeah.
Yeah, that isolated point, I'm not entirely convinced that's the case.
Because 6 comma 18 is a point on f inverse of minus 108.
Oh, yeah, yeah, of course. That is the starting point,
Yeah.
right?
Yeah, yeah,
That is
yeah.
there, but whether it's isolated is the question, right?
Yeah. So let me run through this once. I think I can fix this.
See, the derivative is, yeah, in fact, it is positive when x is less than 6. So that means that you will get solutions. Yeah, in fact, your proof will show that it's not isolated. So derivative is positive. So for x less than 6, the discriminant will be positive. So you will get values of y.
I think what the mistake I
So your
made is
graphing
in
app
the
is,
expression. So I'm just doing that again. I'm deriving it again.
oh,
Yeah.
okay.
Mm,
Minus 108, right?
yeah.
Minus 108. So the quadratic is y squared minus 6xy plus x cubed plus 108 equal to 0. Minus b, so that's 6 b squared minus 4ac. So that is x squared 4 times cube plus 108. Yeah, I don't know how we got this actually.
Mm.
Four. Oh, maybe you took out 4 common. Okay. 4. Okay, yeah, you took out 4 common. So yeah, that's fine. So 9, so 3, 9x squared minus x cubed minus 108. No, that's correct.
Yeah. The expression is correct.
Yeah, so I would suggest you check this.
I I think what I did is like I assumed the graph was correct and I got this quadratic. I'm like, of course, this has to have no solutions, and I just wrote it
Yeah,
down.
that's because you are implicitly trusting of the graph.
Yeah, yeah.
In fact,
Hmm.
for polynomials like this, I don't think you will get isolated points. Possible to get isolated points.
So what you're saying is that f inverse minus 108 is actually embedded.
No, I'm not saying it's embedded. I'm saying that it is the you don't get an isolated point in the inverse image. That's all I'm saying.
Ah, okay.
I mean, I think I am again. I don't have a.
So the
Uh,
failure has to be something similar to. like the self-intersection, right? If it can't
Yeah,
be.
but first figure out what exactly it is, correct? The
Yeah.
correct thing before speculating. I might be wrong also, but see,
Hmm. Uh,
for example, it is possible to get an isolated point. For example, say you have a basically you have a polynomial equation, right?
yeah.
And suppose it factors as x minus 6 squared
Yeah.
plus y minus what are the 2 points? X equal to 6 and y is
18.
80 plus x minus 6 whole square plus y minus 18 whole square, whole thing within brackets into something equal to
Hmm.
0. If it factors like this, obviously the first factor is 0 if and only if x is 6 and y is 18. That would be one
Yeah.
component. Yeah, it is possible. I mean, a priori, there is no reason why you can't have an isolated point. So it is possible, certainly. Yeah, that polynomial for that, yeah, try factoring that x cubed minus 6xy plus y squared equal to minus 108. If you get a quadratic factor like this, x minus 6 whole squared plus y minus 18 whole squared,
Hmm.
multiplied by another one, the other one is what is giving rise to this green curve that you see. Should, yeah, but that's a bit doubtful because the other,
Yeah, I'm not seeing any. What would be the factor? Like x minus 6.
no, they again use one of these factoring, Google itself should be able to factor.
Hmm.
No, just say polynomial factorization of.
Wolfram alpha would give the correct thing. Uh, yeah. What's happening? Ah. Uh, Factorize, what was this thing? Y
Cube
square
minus, yeah,
6xy plus x cube plus 108.
yeah.
Mhm. No, no factorization. It just gave a plot. Yeah, I don't think there's a nice factorization for this. Like if there was a factor, if there was a linear factor, then we would see a like straight line in the graph,
Mm.
which is I don't think that's happening here.
Anyway, it has drawn.
I like it is pretty clear, like the circle that's happening here. Yeah, that's at x equal to 6, and this stops at x equal to minus 3. This thing. Uh, yeah, I think this is exactly x equal to minus 3.
Well, the argument you gave
Hmm.
clearly shows that, uh,
That there are solutions to
yeah,
the depth
that
of 6.
yeah. So why is this messing up? I don't know. Well, you've taken C. Yeah, okay. So C. So it may not be an isolated, again, it might be a double intersection, it's an intersection.
Hmm.
Yeah, exactly. See, for x equal to, that's right. So for when x equal to 6,
Hmm.
it's only one value of y. But for,
Oh, I'm sorry. But the derivative was 18x minus 3x square, right?
yeah,
And at x equal to 6, it is 0.
yeah,
And if you take the double derivative,
yes,
that's minus 6x, which
yes,
again at 6 is 0, is negative.
yeah,
So it is a maxima.
yeah.
So if it's a
No,
maxima,
it's not a maxima. It's the derivative is, yeah, right. It's a, right, yeah. So,
it is a maxima, yeah, because this first derivative is 0 and
so of
second
what?
derivative is
Of the
negative.
you're talking about the discriminant.
Yeah, 9x square minus x cube minus 108,
Yeah, the derivative is 18x minus 3x squared.
which at x equal to 6 is 0.
Yes,
And the second derivative is minus 6x, which again at x equal to 6, it is strictly negative and in the neighborhood also.
yeah,
So this is a like a strict maxima.
yeah.
Yeah, so this is an isolated point. Yeah.
No. But derivative, you can see, no, 1 second. The derivative is 3x into 6 minus x, right?
Yeah.
And if x is less than 6, it's clearly positive.
Yeah, that makes sense, right?
Yeah, that's fine. Okay.
Because
So,
it's
yeah,
increasing up to zero
yeah,
and
yeah,
then
it is
decreasing
leading
after
up to,
zero.
yeah. So it's, so that means, yeah, okay. Yeah, no, you're right. Yeah. Got confused.
Yeah, I confuse myself. Yeah, this
Yeah.
is.
You know, you're absolutely right. So it is, it looks like, yeah, it is a parabola, yeah, which touches the x-axis at x equal to 6, right?
It's a third degree thing. Yeah, it touches it at both x equal to 0 and x equal to 6.
Yeah, x equal to 0 and x equal to 6.
And x equal to 6, it is local maxima, and x equal to 0, I'm not sure.
So the second derivative is minus 6x. So it is strictly negative at x equal to 6. So yeah, oh, that's interesting. So that means it is an isolated point.
Yeah.
That's very weird. Isolated. So that means that,
I'll stop the screen share.
okay, yeah, okay. Actually, Morse lemma in this case should tell you that since the Hessian is non-zero, in fact, the Hessian will be, well, Hessian of the original function. Oh, yeah. The Hessian, correct. The Hessian will be, yeah. The Hessian
Hessian was
anyway,
that, right? 6x minus 6 minus 6 2.
yeah, that's right. So the Hessian will have, so the trace of the Hessian, I think it'll have two positive eigenvalues. So,
Yeah, I think the
so the
eigenvalues
function
at
might
x
have
equal to
an,
6, they are 19 plus minus root
I think
280.
what will happen is, yeah, this function, this point might be a local max or local min, strict local max or local, isolated local max or local min of the original function.
Yeah.
In fact, that 3D plot that Wolfram gave might
Hmm.
show that this is the, if you draw the full graph of this function in 3
Yeah, it will be a local maxima. Yeah.
so that will be
Yeah.
the level set corresponding to -1. Yeah, okay, that's
Yeah.
possible. Okay, fine.
Yeah, my question was like, is there a way to find out which kind of failure is occurring?
Which
Using
kind
some
of
of the,
what?
like, without going through all the calculation, because the failure in both the cases, F inverse 0 and F inverse -108, that's very different.
Very different. Yeah. Yes, there is. In fact, the second derivative should tell you that. That is called a double point, that when two curves intersect,
Hmm.
that should be distinguishable from this, because there, yeah, at what, yeah, see, at that, there, if you calculate the Hessian, 6x minus that thing, what was it? 6x
Minus x 2.
minus x minus x2. So at the 0, 0, well, at 0, 0, it would still be non-singular.
Hmm.
It's a saddle point. Yeah. See, Moore's lemma basically tells you by looking at the eigenvalues of this Hessian,
Hmm.
it says that you can change coordinates near that point and that near the singular point, so
Yeah.
that the function looks like is actually literally equal to a quadratic in x and y, and where uh, an expression of the form x squared plus ax squared plus bxy plus cx squared.
I think the most lemma doesn't give any mixed terms. It only gives x squared and y
Oh,
squared.
right, right. Actually, in fact, yeah, you can even make it mixed up. So ax squared plus by squared.
Yeah, that's very strong. Yeah.
Yeah, and a and b are precisely the eigenvalues
Hmm.
of the Hessian.
That can give the isolated point
Hmm?
because x squared and y squared are positive.
Yeah, that can give isolated point if this both eigenvalues are positive, for example. Right. And
I can give
no,
that
that should
point
also give
also. Yeah,
you,
if
no,
one
one
is,
second, that should also give you, yeah, but that won't help you detect double points.
it can help detect the intersections also. Like if one is positive and one is negative, then we can get like that will be like some x squared minus cy squared, which will be a union of two lines.
Yeah, right, correct. Yeah, in fact, that's what's happening see, at the origin,
Yeah.
no, still origin, the determinant is, oh yeah, minus 36, right. Trace is 2. So the eigenvalues have different signs because the determinant is negative.
Yeah. So you can get this like
So
in general you can get this cone type thing.
yeah, so it will be like a hyperboloid x squared minus, the function will look like x squared minus y squared equal to some c.
And that will always have this singularity at the origin.
Yes. And that, no, more importantly, it will have this kind of double point.
So does this characterize all of these failures? Because if all eigenvalues are positive, then this is very clearly like just a smooth manifold.
This kind of analysis will work only if the Hessian is non-singular.
Yep.
Because
Okay, let me
otherwise
see.
it's very difficult to characterize singular points of, that's a whole theory of that.
Right.
This Arnold's, the Russian mathematician Arnold worked on that, describing singularities of smooth functions in general, but that is very tricky. This is a simplest case when the Hessian is non-degenerate. And then
Yeah,
more
so, but in this particular case, like if we just assume that the Hessian is non-zero, then we can characterize all the failures that can happen.
assuming Morse lemma, but without that you have to do it by hand. Otherwise, how would you? It's not. You can't see directly what the level set looks like.
Yeah. Like assuming most because visually I had a very hard time. Like I thought like I tried sketching it by hand, tried to do like without the graphing calculator. I didn't like I don't know I couldn't do it.
Yeah, you're right. I mean, see, even I was confused for a moment. That I thought that I was a bit surprised that you got an isolated point. So it's not so obvious directly. I mean, there's no simple trick to uh, see what happens when without either using Morse lemma or graphing calculator, just by first principles. I don't see how one can figure out what kind of level set one gets.
Because like Professor Ramsey asked the same question like when he took the smooth manifolds course, like the same exact question.
I see.
And at the time I couldn't do it. Like the inverse thing. Like of course everyone did. They applied it and they got 0 and -108, and they said that that's done because they assumed that the reverse implication is true. But yeah,
I think when people ask this question, they may not even have thought, I don't know whether Vamsi did or not, but people may not even think of this possibility that rule out explicitly the, it's meant more as a director. I certainly wouldn't have asked it in this course. I would have phrased it, I think it's an oversight that I asked it in this form because I don't expect these students, since I
Yeah,
don't know any,
this is not the introductory level question. I don't think.
yeah, though it's elementary in the some sense that it's just about sketching the graph of a function, implicitly defined function, essentially, right? It's implicitly defined in terms of x and y. It's so in that sense, it's completely elementary. You have to draw this graph, but that wasn't my intention.
Yeah.
So I just wanted them to. The better way of phrasing the question is uh, without explicitly mentioning the regular value theorem. No one has to mention the regular value theorem.
Because in the same assignment, one of the questions is a counterexample to the fact that, oh, the regular value theorem fails, but still it's an embedded sum manifolds.
Yeah, right. Yeah, that serves a purpose, but this one,
And we could just explicitly try, you don't need to show the converse. So
yeah, one has to invoke, one has to in the question itself say explicitly, what are the values of x and y? What are the values of C such that F inverse C is a submanifold according to the regular value theorem?
Yeah.
That's then that there's no ambiguity. You just figure out where the gradient is non-zero.
Yeah.
Because I didn't have this in mind. Yeah. I myself was surprised that we get an isolated point. So it's unfair to expect them to do it.
Yeah.
Okay, Avril, anything else?
Not really. I mean, it's going pretty well. I'm
Okay,
still
great.
getting a few AI assignments, but they're reduced like
Yeah.
drastically, so that's fine.
Yeah, just let them know that you know it's AI.
Yeah. I just write I can't like check AI work.
Yeah.
I
Oh, you
just
explicitly told them that. Okay.
yeah.
It's very tempting not to, but what's the point, right? If you in a basic course like this, if you end up using AI.
I mean, even if they ask AI the question and then write it by hand, I think that's good enough. Like at least
Yeah,
they have learned
directly
something.
outputting what it says is ridiculous. That I would have no sympathy for that.
Yeah.
Consulting AI is okay, but writing the same crap is not okay.
Yeah, because some people I can see like this the what's that oh, what do you call it, ALT, the alternating yeah, you take a text
Ah,
and you make it a
yeah. Mm.
yeah, and people have used the wrong definition for it, like you use the one with the 1 by k factorial, but they haven't used that because probably they're seeing it from somewhere else, but even that's fine. Like I cut a few marks for like you use the wrong definition, but still
Yeah,
like they did the effort of trying to find the answer. At least that's good
yeah.
enough. In the final exam, we'll get to. Oh, one more question. For the final exam, when will I get the paper like beforehand, and what's the time period for the checking? Do you know that?
Uh, I can send you the paper, but what's the time period for checking? You have to ask the NPTEL people.
Yeah, because it's first November, right? I can do it in the first week of November. Yeah, I think yeah, that should be
First week of what?
November.
November.
It's on first November the exam, so I can check all of them by the first week. I'm assuming there's
Okay,
16 people going to give the exam.
okay. Yeah, but just ask them that how long, what time we will have to check.
Right. Okay.
I can send you the paper beforehand. I can ask them. And, yeah.
Yeah, yeah. Yeah, so I can create an answer
Yeah, sure.
it myself, yeah. And I'll upload that at the end.
Okay.
Yeah. So I think that's it. Yeah.
Yeah.
Assignments are going well, like there's no issue in the
Okay.
checking.
Great.
Yeah.
Where are you now?
Like I'm in ISC, yeah.
No. What is this place where you're sitting?
Oh, this is my room.
Room means your office room.
No, I mean it's kind of big for an ISC room. Like I'll just put a board here.
Oh, you mean your hostel room?
Yeah, yeah, yeah.
Oh, I see. Oh, it looks
Yeah.
really spacious. Okay.
This used to be a married apartment, so the rooms are like quite big.
Oh, I see. Okay.
Yeah,
Okay, great.
yeah. But this really helps a lot. I mean having the blackboard.
Okay.
Yeah.
Okay. Okay, fine. Yeah.
Yeah.
Okay. Bye.
Yeah. I'll see you. Bye.
Bye.